differentiation and integration of Laplace transform. Yeah. So we have some more properties, features we need to learn for this Laplace transform. Yeah. So this part, yeah, we will learn differentiation, integration of Laplace transform. Yeah. So some of you may still remember we did, Laplace transform of derivative and integral, right? Yeah. So here it's different. The derivative integral we did is at the time domain. Yeah. F function, right? F function, little f function. Now, differentiation integration at the Laplace S domain. Yeah. The capital F function on capital F function. Yeah. So the different side. Yeah. Little f, we did little f. Differentiation integration on little f. Here we need to do differentiation integration on the capital F. Yeah. So the formulas will be different. All right, B.1. First, we need to study a special operation called convolution operation. Yeah. So that's a very useful operation. Yeah. First, let's look at the definition of the convolution. Yeah. Convolution operation. Yeah. Right. Yeah. So let's make some observation. Yeah. First, we know the Laplace transform, the definition we use integral, right? Yeah. So the integral operation has the linearity property. Yeah. So here we can, based on the linearity property, we have this simple property. Okay? All right. Yeah. The function whose Laplace transform equals the function equals the sum of the Laplace transform. Yeah. So that property, very simple. All right. Then of two functions. So, yeah. All right. So then the new question now, we want to generalize this property from sum of two functions to product of two functions. Yeah? So mathematicians, when they try to discover some new properties, yeah, so they usually use the analogy. Yeah. So here we want to see Laplace transform of what function equals the product of the Laplace transform of each function. Yeah. Individual functions. Yeah. Yeah. Yeah, so that's the, by analogy, right? Yeah. So people try to discover some new properties by analogy. Yeah. Yeah. First, we want to try, is it in that question mark? Is it this product of these two functions? Yeah. Yeah. All right. Answer is no. Yeah. Because we can find a counterexample easily. Counterexample. All right. Yeah. Then there is a convolution operation of these two functions. So what's that? We use this star notation, yeah, because it's different from product. Okay, yeah. So it is a special type of combination of two functions, yeah, but not in a straightforward product way. In some special way, although still using the product, but we need to use integral to define this operation. Yeah. So the definition is integral from 0 to t, then the inside integral f of tau, yeah, the dummy variable we use tau, yeah, t we treat as a constant. Yeah. Here in this integral we treat little t as constant. Yeah. So f of tau times g of t minus tau. Yeah. So the product in this special way. Yeah. So this is the definition of this convolution operation. Yeah. So this operation is very useful. It has some nice properties. All right. Then the convolution theorem. Now, we have this nice convolution theorem. If two functions f and g satisfy the assumptions existence theorem Laplace transform. Remember that bound, right? Yeah. So yeah. So we use that bound. Yeah. Let me just f capital M e to the k t. Yeah. So if we use t here. Yeah. Bounded by this exponential function, yeah, with constant m and k. Yeah. Then we know the Laplace transform of that function exists. Yeah. So both little f, little g satisfy that special bounding function. All right. Then, so capital F, capital G exist. Then product. So this time you can see we do product, but at the capital F G side, not at the little f G side. Yeah, so here you can see still product, but not the product is not at the little f and the G side. The product appears at the capital FG side. Yeah. So yeah. So then this capital H is the Laplace transform of this little h. Yeah? Little h, yeah. Yeah. So we can calculate this little h by the definition of convolution in this integral definition. Yeah. Then you calculate the Laplace transform of this little h, it equals the direct product of capital F and capital G. That's the convolution theorem. It can be proved easily. Yeah, the proof can be proved easily. Yeah. Yeah. So we will see the proof quickly. All right. Simple example using convolution theorem. Yeah. All right. Yeah. Yeah. So, by the way, later when we study the Fourier transform, we also have a convolution theorem with respect to Fourier transform. Yeah. Yeah. Same form. Yeah. The form same, but we use Fourier transform. Here we use Laplace transform. Yeah. All right. Let capital H equals, you can see the product structure, right? See? From the capital side, yeah, Laplace transform side, you have a product structure. You can split. Can you split as two functions, product of two functions? Yeah. So find the H, although we can find H directly, right? Yeah. So because this example is so simple, so can you find the Laplace transform directly? Yes. Yeah. Very easy. Yeah. All right. Yeah. So now we need to calculate inverse Laplace transform of this capital H function. All right. All the way. Yeah. So let's do all the way without using the convolution theorem. All the way. Yeah. So because we want to verify, yeah, using two different ways to get the same result. We verify it. All the way, we split the fraction 1 over parenthesis s minus a times s in the difference of these two fractions. Can you see? See it, the split quickly? Yeah? The split quickly? Yeah. If you need to use the partial fraction technique, yeah, you can. Most students apply the partial fraction. Yeah. Capital A, capital B, things like that. Yeah. So you can do that. Yeah, but you need a little more time to calculate, right? Yeah. When you do it, you need to use a little more time. But if you have experience, yeah, because when we split, here, I remember I talked about the split before, yeah. So if you couldn't remember, so usually when I do split on this fraction, yeah, because it's so simple, product of two linear functions of S, two linear functions, yeah, all right, and you can see the difference of these two functions is a constant, yeah. The difference, S minus A minus S, the difference is a constant. Yeah. When you see the property like this, then you have some easy split. Okay. All right. Yeah. But when you do the split should be the difference of one fraction minus another fraction. Difference of two fractions. Yeah. Not summation. At what time the split you use addition, not the difference. Yeah. If the sum of these two functions is a constant, yeah. For example, when you have 1 over A minus S times S, okay, then the sum of these two functions is a constant. Then you use addition. Okay, if the difference of these two functions is a constant, then you use subtraction. Okay, yeah. Here the difference is a constant, so we use subtraction. All right. But when we use subtraction, then which fraction subtracts the other fraction? Well, so you need to consider that. Yeah. Yeah. So to get a positive expression, so we want to use the fraction with the smaller, in the form, smaller denominator to subtract the formula with larger denominator. Yeah, here, so you just treat A as a positive number. Okay, so S minus A, the denominator is smaller than S, right? Yeah. So when you do subtraction, you do 1 over S minus A subtract S. Okay, yeah. So that's the first round split in this way. So there are several factors we consider. All right. You need some experience to get used to this splitting way. All right. But after the split, you need to make adjustment. Yeah. So you need to do common denominator. Yeah. So the numerator part, first one you have S. Then the numerator of the second one minus A. So then the numerator part is A. Yeah, not a 1. It's an A, not a 1. So then you need to make adjustment. Multiply 1 over A to make it balanced. Yeah, because the numerator is A, right? So that's why you need to multiply this 1 over A to balance your result. Yeah. That's why that A, 1 over A, you multiply to each denominator. Yeah, so that's, some quick way. You do the split. Yeah. 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 All right. Then we can take Laplace transform of each term. Yeah. Constant power, we factor it out. Then inside, basic formula, right? So remember, 1, Laplace, yeah, Laplace of 1 equals 1 over S, right? Yeah. So that's simple formula. Yeah, our first basic formula. All right. Then, the inverse part, there is a shifting theorem, right? Yeah. 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 All right? Yeah. So shifting theorem. Yeah. So here, our first shifting theorem, not second. Second, we have the Heaviside function. We need to use Heaviside function. So this is the first shifting theorem. No Heaviside function is used. Yeah. So then we can write result. Yeah. All right. Yeah. So the two terms. Yeah. The result. That's our old way. Yeah. Without using the convolution, so we can calculate. Yeah. Not very hard. Yeah. But the second way, we want to verify convolution theorem. Yeah. So now, at the S side, we split it in the product form. Yeah. The first parenthesis corresponds to f function. Second, g function. Yeah. All right. Capital F equals the first parenthesis. Capital G, second parenthesis. Yeah. We can find little f, little g easily, right? Yeah. Yeah. The basic formula, first shifting theorem. Yeah. So there, yeah, because after this, we have this capital H equals capital F times capital G. Little f, yeah, 1 times that e to the at, yeah. So, yeah, right, yeah. Then little g is 1. Yeah, yeah, this formula, 1. All right. Now let us do convolution of little f and little g by its definition. Yeah. All right. Little f, little g. Yeah, g is 1. Okay. Yeah. So then, g is gone. Right? G is 1. Yeah. So we only need to calculate integral on this e function. Yeah. Then 1 over a. Yeah. So you can see the same as our first way result. Yeah. 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 Although it's not a proof. Yeah. The proof also pretty easy. Yeah. Yeah. The proof also pretty easy. Yeah. All right. Then, all right. So calculate this one. Another one, we can use the convolution way. Yeah, square. We can do a function convolution with itself, right? Yeah. F convolution with f. Yeah. Same function. Yeah. Yeah. F is sine function. Yeah. Sine function, yeah. So sine function do convolution with itself. Yeah. Yeah. Convolution with itself. Yeah. All right. Yeah. So here I think, the calculation part is not hard. Yeah. So yeah. So we just do on the scratch paper. Yeah. All right. Yeah. Yeah. So before I move to the next slide, yeah, I want to ask one question. For this example, yeah, inverse. Yeah. Yeah, for Zoom size students, let me write a little bit. So for this example, inverse Laplace transform on this function, 1 over the denominator s squared plus omega squared parenthesis another square. Yeah. This function, think about, if we do not apply the convolution theorem, how to calculate it? Yeah. Is it easy to calculate it? Yeah. Right? Yeah. So think about that. Yeah. It may not be easy to calculate it, right? Yeah. Yeah. So that's square. How do we get that square? Right? Yeah. 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 We need some technique. Yeah. Yeah. So it may not be that easy. Yeah. Yeah. So we need some, special technique to do it. Yeah. All right. Yeah. But if we apply the convolution theorem, then much easier, you can see. Yeah. All right? Yeah. Now let me move to the next slide. More understanding on convolution. Yeah. Basic properties. Yeah. Yeah. Commutative. Yeah. Commutative. commutable. Yeah. 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 So if just like product, yeah, just like a product. So if you switch f and g, you get the same result. Yeah. Commutative law. Yeah. Yeah. We can call it commutative law. All right. Yeah. All right. Then linearity. Yeah. So with respect to each operand, yeah. So we have the linear, distributive law. Yeah. Yeah. Distribute. Yeah. So there, combination, right? Yeah. The associative law. Yeah. So the basic operation. Yeah. All right. And also with zero, easy. Yeah. All right. Yeah. But some unusual properties of convolution. So the above, they are usual. Yeah. Usual properties. Yeah. But there are some unusual. F to convolution with 1 not equal to f in general. Yeah. Not like product, a function. If we do product with 1, still the same function. So this tells us the convolution is different from the product operation, the property-wise. Yeah. Yeah. How to see it? Yeah, because based on convolution, the convolution with 1, it's like this one. And the derivative of this function equals f. Yeah. So definitely this function in general cannot be f, right? Yeah. Then another one, unusual. Convolution with itself may not be non-negative. Yeah. Yeah. Because if we look at the product of function with itself, f squared, it's non-negative, right? Yeah. But the convolution is different from product. Yeah. If we do convolution with itself, may not be negative, non-negative. Yeah. So here a simple example. Yeah. 1 minus t, do convolution with itself. Yeah. So after calculation, you can see we get this polynomial, and you can see it may not be non-negative. Yeah. So t, you take a negative, small negative number. This side positive, t still negative. Yeah. Yeah. All right. Then, now we want to solve integral equations. Solving integral equations, you can see if you solve directly, it may not be easy. Yeah. All right. Yeah. Solve the Volterra integral equation of the second kind. Yeah. Some special integral equation. Yeah. Y of t minus integral y of tau times sine of t minus tau, yeah, equals t. And you can see this is a convolution structure, right? Yeah. Convolution structure. Yeah. So think about if you do not use the properties of convolution operation. Very hard to solve, right? Yeah. Yeah. How do you separate y function and a sine function? Inside integral, how to separate? Yeah. But now, if we apply the convolution property, yeah, so we can separate. Yeah. We just apply Laplace transform directly. Yeah. So each term, little y, we get a capital Y. Yeah. Convolution, right? Yeah. So capital Y times Laplace transform of sine function. Yeah. Yeah. Sine function. Right hand side, Laplace transform of t, 1 over s squared. See? Yeah. Very simple. Yeah. Then we solve this algebraic equation. Yeah. And then we find the capital Y. Yes. Yeah. Then we split into 2 fractions. Inverse Laplace transform of each fraction, very easy. Yeah. We have the basic formula. Yeah. Basic formula number 4. Okay. Yeah. n plus 1, yeah. So little n plus 1 equals, the first fraction equals 2. So n equals 1 for the first. For the second fraction, n equals 3. Yeah. Yeah. So now you can calculate. So the first one you get a t, the second one you get a 1 over 6 times t cubed. Yeah. Yeah. N factorial, 3 factorial, right? 3 factorial is 6. So you do division to this side. So 1/6 times t cubed. Yeah. Yeah. So little y, you can find the solution. Little y, this function easily. Yeah. Yeah. So you can see this convolution tool, yeah, is very useful. Yeah. Yeah. All right. Yeah. B.2. Now let's study this topic: differentiation and integration of Laplace transforms. Yeah. All right. First, let's look at the differentiation of the transforms. Yeah. At the capital F side. Yeah. Start with the definition. All right. Yeah. Yeah. So this is our original, Laplace definition. Yeah. But we need to work on it. Yeah. We need to work on this formula. But when we work, we want to take derivative both sides. How about that? Differentiation. Differentiation on the capital F side. So let's take derivative directly on capital F. What will we get? Yeah. Then remember, in one of the topic we studied before, when we take differentiation on this integration, there is a consideration, interchange. Yeah, we call it interchange, integration, and differentiation, right? Yeah. Here you can see we need to do that interchange another time. Yeah. Yeah. But we need to assume, some, nice condition. Yeah. All right. Yeah. So here, let's do left-hand side, capital F prime, but the right-hand side, we do derivative with respect to the variable little s. Yeah. There, here, you can see, we do the interchange directly. So we do derivative inside. Inside, the little f function part, we treat as constant. So the only the variable part we do derivative is this e function part. Yeah. So interchanges. So you do the differentiation inside this integral. Yeah. We assume the function is good enough, so we can do integration. We can do the interchange. Yeah. All right. By chain rule, right? Chain rule. Yeah. So here the chain rule. T, we treat t as constant. Okay. Yeah. Do derivative with respect to little s. So negative t, the chain rule thing. Yeah. So that. Yeah. You get that. All right. Yeah. So then you can see equals negative Laplace transform of t times little f function. Yeah. Because based on the definition. So t times that function. Yeah. All right? Yeah. Yeah. Here, yeah. I hope you, yeah. So here, one little thing. Yeah. Here, one little thing. I hope you do not get confused. All right. Because inside this integral, that little t we use as the dummy variable, right? So inside it, we use dummy variable. So that means you should treat this integral limit t and inside the dummy variable, treat as different. Yeah. This upper limit of integral, you treat it as a constant. Okay? You treat it as a constant. Yeah. 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 So here, yeah. For example, in order to avoid confusion, sometimes people put a notation slightly different. For example, this t, you put a t tilde. Okay? So try to make it different, look different with the inside. Inside t, yeah, it's a dummy variable, so you have no problem. But that t, yeah, outside t, that t, yeah, you treat it as a constant. So you want to make it slightly different. Yeah. Right? Yeah. But here, yeah, but for many mathematicians, yeah, many times they do not differentiate it. So they still use the same symbol, yeah, but they know they won't get confused. Yeah. They know how to use these symbols. Yeah. For most mathematicians, yeah. So they many times they do things like this. Yeah. For non-expert, you may get confused. Yeah. But for those experts, they won't get confused. So they do things like this. Why is that? So that's a typical way. So math people, so they do like this. They abuse the notation. Abuse the notation. Yeah. You did something, you know, that may cause a problem, but they can handle it. So they said, oh, in this situation, so we abuse the notation. The reason is they don't want to introduce a new symbol. Okay? They don't want to introduce a new symbol. Yeah. You know, sometimes they want to, you know, make it look simple. So they abuse the notation. Yeah. So that happens frequently. Yeah. Yeah. All right. But you need to know how to separate. The roles are different. Then you can abuse the notation. Yeah. Yeah. All right. So, yeah. So that's we get the first property, first theorem, right? Differentiation theorem property. Yeah. All right. So then we can write the formula. Laplace transform of product of t and the f function. Yeah. T f function. Then this side negative derivative on capital F. Yeah, so that's the first formula. Okay? Then we can also write a inverse Laplace transform version on that formula. Yeah? Yeah? Yeah. So that's different from our t-side derivative formula, right? T-side derivative formula. But there is one thing similar. T side and S side, yeah, two different sides derivative. One thing is common, that's the product. Yeah, because when you apply Laplace transform on little f derivative, you get S side product, right? S times f function. Yeah, but there is the sign is different. Yeah, sign is different. All right. Yeah. So here, yeah, the good thing is you can apply this formula, you can calculate, yeah, see, some relatively complicated, you know, Laplace transform, or inverse Laplace transform. Yeah. Yeah. To calculate this one, for example, yeah, yeah. Remember the previous slide, I asked you how to calculate that. With square. Yeah. Without using convolution, it's pretty hard, right? Yeah. But now we can apply derivative, right? Yeah. F derivative, think about if we apply derivative, one over s squared plus omega squared. Derivative. Will you get the denominator square, yeah, parenthesis square, yeah? Yeah. Although chain rule you get some s, right? Yeah, chain rule you get some s, yeah. So you will get things like this. It may not be one, but like that. Yeah. See, yeah. But derivative, yeah. So you can do more. Think about with this formula, with that formula, we can do more. All right. Yeah. So here, yeah, think about, yeah, because we can apply derivative. Yeah. Yeah. All right. Yeah. So here, the original formula Laplace transform is this. Yeah. Then we calculate by this formula. Yeah. Laplace transform t times, yeah, this function. Yeah. Take derivative, negative derivative on that one. Yeah. That's that. Okay. Yeah. Then to get this one, you can see very close to get the second formula, right? You just do division by 2 beta, 1 over 2 beta. Yeah. But here you can see this formula. Yeah, because I took the screenshot from our textbook. But here you can see something, a t missed, right? Here, a little t is missed. Because here we need to do Laplace transform little t times sine of beta function. Not just sine. Yeah. So we need to put that extra t there. Yeah. Yeah. So here you can see, yeah. So we can get this formula. Yeah. All right. Then, yeah, so here you see, yeah. Yeah. All right. Then, oh, yeah. Yeah, I only have, yeah. Not too much time, yeah, but the integration formula is not complicated, similar to the differentiation, yeah. So I think we can see that formula, yeah. Before the end of today. Integration of the transforms. Yeah. All right. All right. So here, the result. Yeah. Yeah. Oh, this Laplace transform of integral. This is our old formulas, right? Yeah. So here I put here to let you do comparison. Yeah. Because our old formula, we take integral at the t side. Then we apply a Laplace transform on that. Yeah. But the new one, we need to do integral at this side. Capital F. This S side. Yeah. All right. Now, let's take integral. Here you can see the dummy variable, people use S tilde. Try to differentiate from the S outside. Yeah? Yeah. 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 In this way, most people understand how to treat them differently. Yeah. All right. Yeah. So the formula is this. Yeah. That at the t side, you need to do division. S side, when you do integral, so t side, you need to do division by t. Yeah. So that relationship still is there. Yeah. All right. So the inverse Laplace transform, that one. Yeah. Yeah. All right. The condition, the limit, yeah, because when you prove it, you need to do integration by parts. Then you need this limit. Integration by parts. Then you need to calculate. You need this part. It exists. Yeah, yeah. So there. Okay. All right. Yeah. The basic conditions. Yeah. Then you can apply this formula. Here we want to prove it. Yeah. So we have a few minutes. Yeah. So we can quickly prove this formula. By the definition, yeah. So capital S definition of the Laplace transform. Yeah. Then here you have double integral, right? Yeah. Double integral. So here there is another important useful theorem. You switch these two integrals. Yeah. Switch the order. Yeah. Switch the order. Yeah. Under certain condition. Yeah. If the function, is not too bad. Okay? Not too bad. Yeah. So the function actually, here the condition is like this. Yeah. If the function is absolutely integrable, Yeah, you take absolute value of the inside function, and it is still integrable, then you can switch the two integrals. Yeah. Yeah, so there is a theorem for that. Yeah. All right, here we apply that theorem. Okay. All right. Yeah. So here you can see, yeah, we swap these two integrals. Inside integral from 0 to infinity, now it becomes outside integral from 0 to infinity, right? Yeah. All right. ds dt we also swap. dt inside, then now it becomes dt outside. ds to the outside, after the swap, it's inside. Okay? Yeah. So by that, Fubini theorem. All right? Yeah. If the inside function is absolutely integrable, then we can swap these two integrals. Then inside, yeah, right? Because when you do the integral inside, this little ft function, it's a constant. Yeah? So you can take it out of the inside integral, inner integral. You can factor it out of the inner integral. Then this inner integral, very easy to calculate. Yeah. So you get that. Yeah. By Laplace transform, its definition, you get this one. Yeah. So you can prove it easily. Yeah. Yeah. But you need some reasonable assumption. Yeah, but our function satisfies that condition, so we have no problem. Absolute integrable, no problem. Yeah. All right? Yeah. Okay. Yeah. So that's what we have today. So the remaining part, yeah, we will complete it next time. Yeah. Still, yeah, so a lot of material next time. Yeah, next time we need more than first half. Complete the remaining part. Yeah. So then part C. Then we will do the linear algebra, solving linear system of ODEs next time.